Hi everyone, welcome to Minute Elements. This video is part of a video lecture series which is aimed at covering few fundamental concepts in mathematics and physics which are considered prerequisite specifically for those students who are planning to graduate in engineering or pure science. However, these concepts are equally important and significant for every student who is already studying in high school or junior college. These concepts are more or less already covered in our lower classes. However, in this video, our aim will be to understand these concepts in a way so as we can use them in higher applications in engineering and science. So let's get started. In this video, I am going to talk about fundamentals of trigonometry. If we dissect the word trigonometry, it is made up of two words, trigonon, which means triangle, and metron, which means measure in Greek. And therefore, trigonometry is defined as a branch of mathematics that studies relationships between side lengths and angles of a triangle. If we look at the initial application of trigonometry, trigonometry was primarily used to determine unknown distances and angles. And I think therefore it is believed that trigonometry is all about triangles. And hence these concepts are taught to us in our lower classes with the help of a right angle triangle. However, trigonometry has much more greater applications and significance in science and engineering. And I believe visualizing these trigonometric function with the help of a unit circle makes it much more easier to correlate them with their applications in engineering and science. Hence, we will begin by developing a basic construct of trigonometric functions with the help of a unit circle, and then give their more conventional definition with the help of a right angle triangle. So let's begin by defining these trigonometric functions with the help of a unit circle. A unit circle is a circle with radius 1 unit and center located at origin 0, 0. Here I have drawn an unit circle with center A. Now let us draw a point B on this unit circle such that AB makes an angle theta with the horizontal. A perpendicular BC drawn on x-axis represents y coordinate of point B. Similarly, a perpendicular BD drawn on y-axis from point B represents x coordinate of point B. Now in rectangle ACBD, since length of AC is same as length of BD, we can say that x coordinate of point B can also be represented by length of AC. Similarly, y coordinate of point B can also be represented by length AD. Now let us imagine what happens to the length of y coordinate as point B starts moving in anti-clockwise direction. Now to understand this, I have shown various locations of point B as point B moves along the unit circle in anti-clockwise direction. If we observe length of BC or the length of y coordinate as theta increases, we can say that at theta equal to 0 degree, since point B is lying on the x-axis, length of BC or y coordinate of point B is 0. Now as theta starts increasing, we can see here the y coordinate of point B also starts increasing. So length of BC or with y coordinate of point B starts increasing. At theta equal to 90 degree, which can also be written as pi by 2 radians, the y coordinate becomes equal to 1. At this position, the point B is lying on y-axis. If we increase theta further, we can see that the y coordinate of point B starts reducing. So y is reducing. Now as theta approaches 180 degrees or pi radian, y coordinate of point B becomes 0 as point B now is lying on x-axis. If theta is increased further, we can see that the y coordinate of point B again starts increasing, but now in negative y direction. And as theta reaches 270 degrees or 3 pi by 2 radians, the y coordinate of point B becomes -1, since point B now is lying on negative y axis. As theta is increased further, the y coordinate of point B starts reducing, and at theta equals to 360 degrees or 2 pi, the y coordinate becomes equal to 0 once again, as point B now lying on positive x-axis. So we observed that there is a pattern in the variation of y coordinate of point P. Now if I increase theta further above 360 degrees, this whole cycle will keep on repeating every time I move around the circle. To understand this variation in y coordinate better, let's try to plot the variation in this y coordinate of point B with respect to angle theta. And let's do it with the help of a graphical calculator. I am using GeoGebra Classic as my graphic calculator. I have drawn unit circle with center A over here. I plotted the point B such that segment AB makes an angle theta with the horizontal. Right now the value of theta is 40 degree. BC represents y coordinate of point B. Now we are trying to plot variation in the y coordinate of point B as angle theta varies when B starts moving along the circle in anti-clockwise direction. This graph has been plotted with the help of segment EF. So EF over here represents the variation in length BC. X-axis over here represents angle theta. The unit of angle theta is in radians. So when I say 180 degree or pi radians, it means the value should be close to 3.14. Now let's try to change the angle theta with the help of this slider, and let's observe how this segment BC varies with angle theta. So I'm playing the animation. Over here you can see the point B is moving along the circle, theta is changing, and the variation in the y coordinate of point B is following a sine function. Hence we can say that for any point on the unit circle, its y coordinate can be represented by sine of the angle theta, where theta is the angle between the radius at that point and the positive x-axis. From the previous explanation, we understood that for every point on a unit circle, its y coordinate can be given by sine of theta, where theta is angle between radius at that point and positive x-axis. For an example, in this position, for point B, such that radius AB making an angle of theta, we can say that y coordinate, which is represented by length of segment BC, is equal to sine of theta. So length of BC, which is equal to y coordinate of point B, is equal to sine of theta. Now let's try to understand what happens to the x coordinate of point B, which is represented by length of AC, when point B starts moving along the circle in anti-clockwise direction. Now to understand this, I have shown various positions of point B as it moves along the unit circle in anti-clockwise direction. By observing the length of AC over here, we can say that at theta equal to 0, length of AC, which is equal to x coordinate of point B, is equal to maximum, that is 1. Since point B is lying on x-axis at this angle. Now as theta starts increasing above 0 degree and moves towards 90 degree, looking at the positions of C1 and C2, we can say that length AC starts reducing. This I have presented on this small
linear scale. So as theta increases towards 90 degree, the C starts moving closer to point A. That means length AC starts reducing. Now at theta equals to 90 degree or pi by 2 radians, at this point we can see that length of AC becomes 0. That means the x coordinate of point is 0. As we increase theta further and move towards 180 degree, we can see that now the point C starts moving away from point A. That means length of AC starts increasing, but this time along the negative x direction. And at theta equals to 180 degrees, that is pi radians, x coordinate becomes -1. At this position, the point B is lying on negative x-axis. Now as theta increases and becomes 270 degrees, that is 3 pi by 2 radians, we can observe that the x coordinate again starts reducing as point C starts moving closer to point A. Length of AC reduces. At theta equal to 270 degrees, x again becomes 0. Now if we increase theta further from 270 towards 360 degrees, the point C again starts moving away from point A. That means length of AC starts increasing, and at theta equals to 360 degree, that is 2 pi, we can say that x coordinate again becomes +1 as point B is now lying at positive x-axis again. If we increase theta further above 360 degrees, it can be easily concluded that the whole cycle explained right now will repeat again. And at theta equals to multiple of 2 pi, let's say 720 degrees, that means 4 pi, x will become 1 again. Let's try to understand variation of x coordinate by plotting this with respect to angle theta as point B moves along the circle in anti-clockwise direction. Again, we'll be using a graphical calculator. So let's plot it.
In this particular animation, we are trying to see how the x coordinate of point B, which is nothing but length AC, varies with angle theta as point B moves around the circle. So I'm going to change theta from 0 to 360 degree with the help of this slider and plotting the length AC with the help of segment EF over here. So let's play the animation and figure out how this x coordinate varies with angle theta. Now again, theta is in radians. Now you can see as point B moves along the circle in anti-clockwise direction, the x coordinate of point B follows a cosine function. In other words, we can say that for every point on a unit circle, its x coordinate can be represented as cos of theta, where theta is the angle between radius at that point and positive x-axis.
So we have understood that for every point on unit circle, its x coordinate can be given by cos of theta, where theta is angle between radius at that point and positive x-axis. For an example, in this position for point B, such that radius AB making an angle of theta with positive x-axis, coordinate of point B can be given by cos of theta, sine of theta, where cos theta represents its x coordinate given by length AC and sine theta represents its y coordinate given by length BC. This result is of great significance in mathematics. Now one more observation can be made very easily from the previous explanation. Imagine if I move point B such that new value of theta can be written as theta plus 2 pi or theta plus n times 2 pi, where n is a positive integer. Now what I mean is, if I rotate point B such that the new angle theta becomes theta plus 2 pi, That means if I rotate point B once around a circle, starting from the original position, the new angle between the radius AB and positive x-axis can be written by theta plus 2 pi. If I move point B around the circle 2 times, in this case the new angle can be written as theta plus 2 times 2 pi. And if I move point B n times around the circle starting from this position, the new angle can be written as theta plus n2 pi. Now in this new position, it can be observed that the x and y coordinate of point B remain unchanged as B comes back to its original position. That means we can say that for angle theta equals to theta plus n2 pi, sine of theta plus n times 2 pi is equals to sine theta, since the coordinate of B are remaining unchanged. That means the y coordinate in the new position is equal to the y coordinate in the original position. Similarly, we can say that cos of theta plus n times 2 pi, that means x coordinate in the new position is equal to cos theta, that is the x coordinate in the original position. Now let's talk about the magnitude of sine and cosine function. If we go back to our previous explanation, when we were trying to understand variation in the x and y coordinate of point B, as point B was moving around the unit circle in anti-clockwise direction, we can observe that the value of cosine and sine functions kind of swing between -1 and +1. Like in this example, when we are trying to understand variation in the x coordinate, we concluded that at theta equal to 0, the x coordinate, which means cos theta, is maximum, which is equal to 1. It became 0 when theta was 90 degree. It became -1 when theta was 180 degree. It became again 1 when theta became 360 degree. We also concluded that if we keep on moving point B beyond 360 degree, the same cycle will be repeated. That means the maximum value a cos theta can take is +1 and minimum value a cos theta can take is -1. Similarly, when we were trying to understand variation of y coordinate as point B was moving around the circle in anti-clockwise direction, we saw that value of sine function, that is sine theta, swings between -1 and +1. For an example, when we started with theta equal to 0, we concluded that length BC, that means the y coordinate is 0. As we increase the theta beyond 0, at theta equal to 90 degree when point B moved to the y axis, we said that the y coordinate becomes +1. It becomes 0 when theta becomes 180 degree. It again becomes -1 when theta is 270 degree, comes back to 0 at theta equal to 360 degree. We also concluded that if we move point B beyond theta equal to 360 degree, this whole cycle will be repeated. That means the value of sine theta swings or lies between -1 and +1. This can be written mathematically as sine theta can take all possible values between -1 and +1 for various angles theta. Similarly, cos theta can take minimum value -1 and maximum value +1. That means cos theta can lie between -1 and +1 for all the possible values of theta. Now let's get into the conventional definition of sine theta and cos theta with the help of a right angle triangle. So let's draw the unit circle once again, and let's show the point B on it. We know that BC represents y coordinate of point B and AC represents x coordinate of point B, and triangle ACB is a right angled triangle. We have concluded length BC is equals to sine theta and length AC is equals to cos theta. Conventionally, sine theta can be defined as opposite side upon hypotenuse. That means in this right angle triangle, if I write this angle as theta, then sine theta can be written as opposite side, which is nothing but BC upon AB. That means BC upon AB. In this case, since it's a unit circle, the radius is equal to 1. Therefore, this becomes equal to BC, as we have concluded earlier. Similarly, cos theta is defined as adjacent side upon hypotenuse. The adjacent side to this theta is represented by AC. That means cos theta can be written as AC upon AB, where AB is the hypotenuse. Now hypotenuse in this case is 1, so this becomes AC, as we have clarified earlier. Now let's try to find out value of sine theta and cos theta for some standard angles. Now in this picture over here, I have shown 4 distinct position of point B. Basically 5 distinct position of point B. For an example, when theta is equal to 0 degrees, that means in position B1, point B is lying on x-axis and its coordinates can be given by 1, 0. In the previous explanation, we have concluded that for every point on a unit circle, its coordinates can be given by cos theta, sine theta. Hence, in this position, when theta is equal to 0 degrees and coordinates of point B are 1, 0, that means cos theta is 1 and sine theta is 0. Now, if we go to theta equals to 90 degrees, that means when point B is in the position B2, which is lying on positive y-axis, its coordinates can be given by 0, 1. That means cos theta is 0, which is nothing but the x-coordinate, and sine theta is equal to 1, which is nothing but the y-coordinate. In the next position, when theta is equal to 180 degrees, that means in position B3, point B is lying on negative x-axis and its coordinates are given by minus 1, 0. That means the x-coordinate is minus 1, which is equal to cos theta, and y-coordinate is 0, which is equal to sine theta. For angle theta equals to 270 degrees, point B is in the position B4, which is lying on negative y-axis, and its coordinates can be given by 0, minus 1. That means the x-coordinate is 0, which is equal to cos theta, and y-coordinate is equal to minus 1, which is equal to sine theta. In the next position, when theta becomes equal to 360 degrees or 2 pi, the position B5 coincides with the initial position B1, as we have already discussed when you move point B such that the new angle can be written as theta plus 2 pi or theta plus n2 pi, sine theta plus n2 pi is equal to sine theta, and cos theta plus n2 pi is equal to cos theta. Hence, in position B5, the coordinates will be exactly same as in B1, that is 1, 0. That means cos theta will be 1 and sine theta is equal to 0. Now over here I have defined a special angle which is written as integer multiple of 360 or integer multiple of 2 pi. Now this angle represents a position which is same as B1 or B5. So for every angle which can be written as integer multiple of 360 degree or integer multiple of 2 pi, the cos theta will become 1 and sine theta will become 0. Now, but there is a question that how do we find out the value of sine theta and cos theta for any intermediate angle? Now, one way of doing this is using the basic geometry and symmetry. So over here I have drawn an equilateral triangle PQR its sides equal to 1 unit. That means length of PQ equals to length of QR equals to length of PR is equals to 1 unit. Now since in an equilateral triangle all the angles are equal, and we know that sum of angles in a triangle is equal to 180 degree, that gives us each angle as 60 degrees for an equilateral triangle. Now let's draw a perpendicular PM from point P on base QR. From property of an equilateral triangle, we can conclude that the perpendicular drawn on QR will divide QR in equal parts. That means length of QM is equal to length of MR, which is equal to half of length of QR, which is nothing but half, since length of QR is equal to 1. A perpendicular drawn from a vertex to a base or to a side opposite to it also divides the angle in an equilateral triangle. That means angle QPM is equal to half of angle QPR, which is equal to half of 60 degrees. That gives us QPM as 30 degrees. That means this angle over here is 30 degrees. Now if we consider triangle QPM, we can define sine of 30 degrees by using the basic definition of opposite side upon hypotenuse as, so if you look at 30 degree, the opposite side is QM and the hypotenuse is PQ. That means QM upon PQ. Now we know that length of QM is half and length of PQ is equal to 1. So this ratio becomes equal to half, or we can say that sine 30 is equal to half. In order to define cos 30, which is nothing but adjacent side upon hypotenuse, so adjacent side for this angle 30 degree is nothing but PM and the hypotenuse is PQ. So this becomes equal to PM upon PQ. So we need to know the length PM. Now we can find out length PM by using Pythagoras theorem. So square of PM plus square of QM will give us square of PQ. Square of base plus square of height is equal to square of hypotenuse. So therefore PM can be written as root of PQ square minus QM square. Now PQ is 1 and QM is half. So this gives us 1 minus 1 by 4, which is nothing but root of 3 by 4, which can be written as root of 3 by 2. Hence length of PM over here is equals to root 3 by 2. And length of PQ, we know that it is equal to 1. Therefore cos of 30 degree becomes root 3 by 2. We can define sine 60 degree also. So sine 60 will be again opposite side, which is nothing but PM upon hypotenuse, which is nothing but PQ. So we can say sine 60 is equals to PM upon PQ. We know that PM is root 3 by 2 and PQ is equal to 1. So sine 60 becomes root 3 by 2. Cos 60 using the definition becomes adjacent side, which is nothing but QM upon hypotenuse PQ. So we can say cos 60 is adjacent side QM upon hypotenuse PQ, which is nothing but half upon 1, which is nothing but half. So from this exercise we can say for theta equals to 30 degrees and 60 degrees, we can write down the value of cos theta and sin theta. So cos theta, for theta equals to 30 degrees, we have calculated as root 3 by 2. So we can write this as root 3 by 2. Sine 30 we have calculated as half over here. So we can write down sine 30 as half. Cos of 60 we have calculated as half over here, so this becomes half, and sine of 60 we have calculated as root 3 by 2, so this becomes root 3 by 2. We can use similar geometry and we can find out sine and cosine value for some other intermediate angles. But it is very difficult to find out sine and cosine for all other intermediate angles. For an example, if we need to calculate sine of, let's say, 30.3 degrees, then it becomes quite difficult. So we need a different description of sine and cosine function.